Okay, so in this video tutorial we are going to be talking about standing waves. Now, with standing waves, we're going to talk about a couple different mediums. We're going to first talk about standing waves on a string or rope, and then we're going to talk about standing waves dealing with sound. Now, standing waves are created when you have a string, or in this case a rubber band, that's fixed at both ends and an oscillation is sent through. So did you see that vibration back and forth, up and down? That is a standing wave. If we were to look at this in slow motion, this piece of rubber band would oscillate up and down like this. And it does this very quickly and appears to kind of sweep out this middle area here. Okay, that is a standing wave. So let's look at some possible standing waves. First, I'm going to draw a string that is fixed at both ends. So these two ends here are fixed. And I'm going to draw my wave with the rubber band that I just did. So part of it oscillated up, and then part of it oscillated down, and it did this back and forth. This is the first harmonic, or the fundamental frequency. Now, these two positions here where there is no movement, those are called nodes. This position here where I have maximum displacement, that position is the antinode. Okay? So, maximum displacement, antinode. No movement at all, node. Now, this m equals 1. That is the, it's called the mode number. And what this tells you is the number of 1/2 wavelengths. So nodes, adjacent nodes, are always 1/2 wavelength apart. So what I have here, m equals 1. This whole string has a length L. And m tells you how many half wavelengths you have across the string. So these are my two adjacent nodes. They are 1/2 wavelength apart, which means I only have one 1/2 wavelength. So m is 1. Now, if m is 1, then that means that my total length L is equal to 1/2 of the wavelength. Because again, this whole length is L, but from node to node is 1/2 lambda, or 1/2 the wavelength. Which means that my wavelength, if I multiply both sides by 2, for the fundamental frequency, my wavelength is 2 times the total length of my string. Because imagine if instead of this wave reflecting back, imagine if it went through like that. And it went through as a normal wave. Well, from here to here would be one whole wavelength. Well, that would be double the length of my string. So that's the first harmonic. Now let's look at, shocker here, the second harmonic. So this is what's going to happen. Our wave is going to come down like this, and then come back, and then whoop, like that. So this is m equals 2. Here's why. If you look, I've got 1, 2, 3 nodes. Okay? Which means there's a 1/2 wavelength, there's a 1/2 wavelength. Again, m is the number of 1/2 wavelengths. So here I have 2 1/2 wavelengths, so my m is 2. Now again, my total length here is L. But now I've got this distance here, 1/2 L, equal to 1/2 of my wavelength. Because from here to here is 1/2 the wavelength. From here to here, if it were drawn to scale, would be 1/2 the wavelength. So now I just multiply both sides by 2, and I get L equal to a wavelength. And you can see the entire wave right here. I go up and crest, and then I trough, and then I come back to the same position. So M equals 2. This is the second harmonic. My L is going to be my wavelength. Now, let's look at the third harmonic. With the third harmonic, I'm going to go up, come down, up, down, and then reflect back, like so. So if you look, I've got M equals 2, and I've got 1, 2 antinodes. Here, I'm at, let me quarantine this off here. Here, this is the third harmonic, or M equals 3, because I've got 1 1/2 wavelength, 2 1/2 wavelengths, 3 1/2 wavelengths, or 3 antinodes. Now, let's talk about what the wavelength would be here. This distance, if the total string has a length L, this little distance right here is always going to be 1/2 of the wavelength. From node to node is 1/2 the wavelength. So let's label that 1/2 lambda. Now, if this total thing has a length L, then this is 1/3 L, 2/3 L, and then 3/3 L, or just L. So this little distance is 1/3 L, but it's also 1/2 the wavelength. So solving for wavelength here, I get a lambda equal to 2/3 L. If you notice, I've got 2L over 3, or my M value. Here, there's the bell, by the way. Here, I've got L over 2, which this simplifies down to just L. My generic equation for wavelength when it comes to the length of the string, it's going to be 2L over M, or my frequency, which will be equal to the wavelength. So for M equals 1, we had a wavelength of, M equals 1, we had across the whole string, like so, this was 1/2 of the wavelength, or 1L. So 1/2 lambda equaled L, or lambda equaled 2L. Look at it with this equation. I've got 2L over M. In this case, M is 1. And I get the same thing, which is usually pretty good. So with standing waves, you can look at how many antinodes you have and get your mode number. Or you can count how many half wavelengths you have. Here I've got 1 1/2 wavelength, 2 1/2 wavelength, 3 1/2 wavelengths. I'm at M equals 3. Okay, so what good is this? Well, all stringed instruments operate under this standing wave procedure. So think about with wavelength being equal to 2L over M. Another equation that we have that involves wavelength, velocity is frequency times wavelength. So if I were to take this and plug it in here, with a stringed instrument, we want to change the frequency of my note. If you change the frequency, you change the pitch that you hear. A higher frequency means a higher pitch. Lower frequency, lower pitch. So changing the length of my string can affect the frequency that I have, because the velocity is always going to be the velocity of sound, unless somehow the temperature in your room changes very rapidly. So changing length can alter the frequency that you hear. So for instance, when you're playing air guitar and you want to play a higher note, you bring your fingers closer to where you're strumming. You shorten that length. What that does is that increases the frequency. So, let's talk about another class of instruments, and let's look at now standing waves in air, or more commonly known as sound. And what I'm going to do is I'm going to start with a tube that is open at both ends. Okay, and with that, you have to imagine that outside of this tube, I've got atmosphere, or just room pressure. And so the sound that's coming in here, at these positions, any tube that you have that's open, the open end can be considered a node, because that sound is going to hit the atmosphere. Part of it is going to reflect out, and part of it is going to bounce back in. So with those open ends, I can make them nodes. So this is the first fundamental frequency for an open-ended tube. So with an open-ended tube, it's really no different than two strings fixed at both ends. Now, why does the sound reflect back? Well, imagine that you've got a very thin rope with a wave going through it, going this way. But then that wave is traveling towards and is connected to a really thick rope, the atmosphere. Well, part of it is going to reflect back. But part of it is also going to make or transfer its energy to the thicker rope. But both are going to be smaller than the original. That's the same thing that happens with sound in an open-ended tube. So when you have sound in an open-ended tube like this, you can really draw, there's the bell again, you can really draw as many frequency or as many harmonics as you want, because it's no different than having a string fixed at both ends. For instance, I could draw the second harmonic, third harmonic, fourth harmonic, so on and so forth. Now, we can also look at sound going through a tube that is closed at both ends. So any closed end should be considered an antinode, because at this point, all of the sound can either maximize or compress against the wall, or all of the sound can jump away from the wall, giving me a very high compression or a very low refraction. So those positions are antinodes. And here's how I'm going to draw this. I've got two antinodes here where I have maximum displacement, and then I have a node here in the middle. So with a closed-end tube, imagine that you take the string that's fixed on both ends, cut it in half, and then copy and paste this end over here. Okay? So closed ends are antinodes. Well, not very many instruments are going to be closed at both ends because it's not very fun and pleasant to listen to. So most instruments are going to be open at one end, closed on another. So think about a clarinet, saxophone, really any instrument that you can think of that you blow air into. You've got an open end where the sound is coming out, and then you've got a closed end where your mouth is. Now, here I've got a closed end on this side and an open end here. Now, I know that an open end needs to be a node, and a closed end needs to be an antinode. So with this, I'm going to draw the first frequency that I can have here. I'm going to draw a node there, and then an antinode at the other end. This would be the fundamental frequency for a tube that is open at one end. Now, if I tried to draw the second harmonic here, in other words, m equals 2, where I've got two 1/2 wavelengths here, I can't really split it up, because if I try to draw a node here and a node here, then I'd have 1, 2, 2.5 half wavelengths. So if I tried to put a node here with this distance apart, well, that would mean I'd need a node here. But this is a closed end, which means I can't have a node there. So we have to skip the second harmonic and go to the third harmonic, like so. So with this, if I tried to draw the second harmonic, I would need a node there, and I would need a node here. What I've got now is I've got half wavelength there, and then I've got another half wavelength here. So I've got m equals 3. Okay? I can't have the second harmonic. Open closed tubes can only have odd harmonics. Okay? I can't draw two 1/2 wavelengths in here, just like I couldn't draw 4 1/2 wavelengths, or 6, or 8. I can only go 1, 3, 5, 7, 9, so on and so forth. Okay? So if you have an open closed tube like this, you're only going to have the odd harmonics. So with your lab, with this experiment, you've got a column that you're going to fill up with water. Then you've got another column, that doesn't work. You've got another column that you can raise up or lower down, effectively changing the length. The length is going to be from this open end to the water, or the closed end. Okay? So what you're going to do is you're going to have your tuning fork above this open end. Strike it, and you're going to raise this up until you hear a very loud harmonic. That harmonic is the interference taking place that's giving you a fundamental frequency. So with that, you'll know the frequency of the tuning fork. You'll be able to measure the length of the air column, and from that, you should be able to calculate the velocity of sound. Again, the velocity of sound is frequency times wavelength. But you've got to think, what is your wavelength now with this open closed-end tube?